Well, welcome back, and this is the last in our little series on entropy, and this covers the last section of the notes looking at Gibbs free energy, or sometimes it's just called Gibbs energy. So you'll need your notes, you'll need a pen, and you'll need a calculator, and we're going to be looking at page 23 of your notes. So you should be very familiar now with these equations. So I've got delta S total, which is my system plus my surroundings, and my surroundings, which is minus delta H over T. So putting that into my equation, I get delta S total is equal to delta S system minus delta H over T. Okay, so the total entropy term, that's fine. I want to know that. That's easy. System, that's okay, that's very straightforward. It's this term that's causing me the issues, the surroundings term. And because this is the entropy change of basically the rest of the universe, basically anything which isn't my system, and that's pretty difficult to measure. It's pretty difficult to do anything with that. So I'd rather get rid of this surroundings terms. What I'd really like to be able to do is to define everything in terms of the system. Because the system is nice, it's compact, it's easy to measure, it's just what is happening to my chemicals. Now, I've got a little trick up my sleeve, and it's to do with signs, and it's to do with my delta H, and it goes back to something we studied in the first law of thermodynamics. So, if you think about an enthalpy change for a reaction, and I'm going to use exothermic as my example. So you've got here an enthalpy change there. So those are my reactants forming my products. And this is an exothermic reaction. So the energy is coming out from those chemicals into the surroundings because the surroundings are getting hotter. That's why it's a minus delta H. Now, we know from the first law that energy cannot be created or destroyed. So we know that the amount of energy coming out into the surroundings, making the surroundings hotter, giving the surroundings more entropy, must be the same as the energy which is being lost by the chemicals. So these two numbers must be identical. The difference between them is the sign. So this is gaining in energy, and this is losing in energy. So all I really need to do to get rid of that surroundings term is to change the sign, because if this is coming out and raising the entropy, well, this will be going down and lowering the entropy. So all I'm actually going to do is to times through my whole thing by minus T. And that's what I've done here. So I've got minus T times delta S total equals delta H minus T delta S system. Okay, notice I've got rid of the sign in front of the delta H. Now this delta H refers to the system, not the surroundings. And because everything is now determined by the surroundings, we drop the subscript. And we give this term here, minus T times delta S total, a new identity. We call it Gibbs. So my Gibbs equation is here. Delta G is equal to delta H minus T delta S. And this has all to do with the system. And that's what makes Gibbs a much easier and more compact thing to try and calculate. Because I don't have to consider what's going on in the rest of the universe. I just have to consider what's going on with my chemicals on my lab bench. So there's a very straightforward relationship between delta G and delta S total. Basically, if delta S total is positive, then delta G will be negative, and vice versa. Negative. And we can see that here from this equation, because all I'm doing is timesing my delta S total by minus T. And the temperature is fixed, that's in Kelvin, and therefore if I've timed, that must be a positive number, that temperature, because it's in Kelvin and I can't get a negative Kelvin. So it's going to be minus number times by the delta S total. So again, if that works out as being negative, then we say the reaction again is feasible. Okay, so we're now going to have a look at a couple of calculations using this equation. So I've got my delta G is equal to delta H minus T delta S. Notice I've dropped all the subscripts here because I'm only dealing with the system. I'm going to be looking at water and whether water can turn into ice at 5 degrees or at -5 degrees. So I want to know, is this reaction feasible at these two temperatures? If I was going to take liquid water and turn it into solid water. Okay, now I know that that reaction is exothermic, and I know that because I'm going from liquid to solid, so I am actually forming more hydrogen bonds. And because I'm making bonds, it's going to release energy, so that's negative. So I want to work out the reaction, is this feasible at this temperature? Then I'm going to calculate it at this temperature. So delta G is equal to -6012. That's the enthalpy change in joules per mole. Take away, and I've got my 5 degrees, which is 278 Kelvin, times by my entropy change, which is -22. And I put those numbers in my calculator, and I get plus 104 joules per mole. Now, just to be annoying, Gibbs is always given in kilojoules per mole, so delta G is plus 0.104 kilojoules per mole. In other words, it's not feasible. And we should kind of know that. We should know that water won't freeze at 5 degrees Celsius. Now let's do the same calculations, but at -5 degrees Celsius. So we have delta G is equal to -6012 again, minus, this time I've got 268 as my temperature, times again -22.0. And I get -116 joules per mole, no Kelvin this time, and that's -0.116 kilojoules per mole. So therefore, that is feasible. So that reaction will work at -5, it won't work at +5. And again, that is something we should be very well aware of, that yes, if we put water in the freezer, it will turn into ice. Now, we need to look at why that might be. So here I've got this nice negative term here. This is an exothermic reaction, so that's working for us. But because we're going from liquid water to solid water, therefore I'm decreasing my entropy, hence the negative sign here. Overall, this term becomes positive. And at 5 degrees, this is quite a large positive number. So it's not enough to outweigh this negative delta H. However, when I drop the temperature, this again becomes a smaller positive number. And at this point, this large delta H value is able to outweigh it. So the last bit of this we're going to look at is this very important little table at the bottom of the page. So if the delta H is negative, in other words, if it's an exothermic reaction, and there is an increase in entropy, this will always work. So this is feasible at all temperatures. Delta G is always negative. In other words, there's no temperature at which I can get this reaction to where it's going to stop or start working. It's always feasible at all temperatures. Likewise, at the other end of the scale, if it's an endothermic reaction, in other words, the surroundings are getting colder, and it's a negative delta S here, if both of those two happen, it's not feasible. Okay, and it's not going to work at any temperature. So it's always going to be a non-feasible reaction. And delta G is always positive. So it's never ever going to work. No matter what I take the temperature to, those reactions won't work. I'd have to think of a different reaction, or I'd have to do what we call coupling. I'd have to connect it somehow to a different reaction, which has a feasible Gibbs value. Now, the two that are interesting are the ones kind of in the middle. So this first one here, I've got a negative reaction. My delta H is exothermic, so that's working in my favour because that's going to increase in entropy. However, I've got a minus delta S, so I want this value here to be as small as possible. I want it to be as small as possible so that I don't get a big positive number. Okay, so this is more feasible at low temperatures because it's exothermic here. This isn't working in my favour, so I want this value to be as small as possible. So I want my temperature to be as low as possible. So more likely at low temperatures. On the other hand, if the delta H is positive and my delta S is positive, well, this is working against me this time because I don't want a positive value there, I want a negative value, so I don't want this to work. So I need this value to be as large as possible in order to outweigh this positive value here. So this is more feasible at high temperatures. So as a general rule of thumb, if you've got an exothermic reaction, as we did with our ice example, you want the temperature to be as low as possible. That will make my reaction feasible or more feasible. On the other hand, if I've got an endothermic reaction, I want the temperature to be as high as possible. And we saw that earlier on when we did the thermal decomposition of the carbonates. That's an endothermic reaction and you had to heat it to get it to become feasible. Whereas in our ice example, we had to cool it down to become feasible. Okay, so that finishes this section on entropy, and that actually finishes the whole notes. So you should have enough details now to be able to complete all the pack notes and all the questions at the end of the notes. And I'd remind you that those need to be uploaded. The questions, not the whole pack, please, by Friday. So that's it from entropy. I hope you've enjoyed these videos. Do also check out our videos on eStream, where we put some about mass spec and infrared spectroscopy. Otherwise, I'll speak to you soon. Take care, stay safe, stay home. All the best. Bye bye.